We're going to complete the electrostatics in the next class, or in another 2 class we are going to complete that. And exactly on 25 we have that is Wednesday in the evening after I think that time is okay. If anybody has issues, kindly tell me, so I will cross check and I will change the time bit maybe later. Okay, so you need just 40 minutes to complete that. It will be around 4-5 more question problem, and that will be covering up, maybe you'll be working about 10 step or less than 10 step size of numerical problems. So, and it will be asked purely within the electrostatics, whatever that is taught up to that day. So most probably I will complete electrostatics by that time. So you can post me, like if you have any class or it is clashing with your other academic sessions or something, so that I will change the time. Okay. Well, yeah, today we are going to see other very interesting set of equations in the electrostatics called Poisson and the Laplace equations. And they are having actually versatile applications in many fields, including the recent works in the black hole all the way actually. So they are actually working on this Poisson equations only. So they use it for electrodynamics as well as thermodynamic applications. So we already started the discussions on various aspects of the electrostatics. It started with Coulomb's law, and we went inside electric field. The electric field is the foundation for the electrostatics and throughout the course. And how this electric field will be induced by different types of charged bodies. And another aspect of the same electric field is flux. So the electric field or electric flux, they are just a representation of our intuition about the how these electric charges or the charged bodies they behave each other. And in reality, whether they are correct or not, or they are they are actually behaving in this way or not, that is a big question, because nobody has seen, not even the electrons. So therefore, the electric field and the associated whatever the mathematical expressions, all these things, they are just going to tell the behavior of the particular medium or the particular the force which is actually acting between two bodies. And in terms of gravity, it is two masses. Like that, here we have two charges, how they are actually going to behave each other. And the theory is so successful because it is true that we are using this wireless device which works simply based on this electromagnetic field theory. So that the theory is highly successful, and the theory is also complete. There is a completeness for a particular theory is available. It's supposed to prove the concept itself by that. So that, for instance, quantum mechanics cannot prove itself it's correct, because it is more than a mathematical work, it is a statistical work. So that is the minor difference between this so-called the field theory and the, that is why Yum theory is coming to rescue that. So I believe all of you have heard about this. So this electric flux density is another version of the electric field, and the advantage is we can easily calculate whatever the difficulties we are feeling in the Coulomb's law. We can use Gauss law to solve that. Okay. And the extension of the Gauss law, we have moved to the potential energy or the work done by a charge in a field. So how to represent that, and the potential difference, and in other way, the absolute potential at any particular point, it's nothing but moving a point charge from an infinite point to the point of interest, to where we have to keep it. So that electrical energy required to or the corresponding mechanical energy to move the charge. So that is nothing but the potential energy. The same potential energy in the in the mechanical case, it is completely different. It is purely depends on the height. Here it is purely depends on the charge, the location of the charges which are contributing this electric field. So in other words, there it is a gravitational field. Here it is electric field like that. So if we are close to the uh, charge which is producing the electric field, I already told about that. If there is a line charge, infinite line charge, and we know about its electric field, so can someone say that it is going to have a charge density of rho L? So the rho L divided by 2 pi epsilon naught rho. Is that correct? Yes. So, and this A row vector. So as we are keep on going away from there, then here the potential will be more, here it will be less, and it will be keep on going at a distance of r equal to infinite. We will be getting electric field at approximately 0. Okay, so from here to here, if I want to move the point charge, what amount of work done uh, has been done? So that is that defines the potential energy. Okay, so many people are simply calling that as a potential. Sometimes it is giving different meaning also. So potential energy is the correct word. So by the way, potential difference is nothing but the energy difference between two places in order to do the extra work to be done to move the point charge or rotate the point charge or spin the point charge, whatever it is. The next very important one is the potential gradient. Like other gradients, potential gradient is nothing but the differential version of the potential itself. It tells about how fast the potential is increasing, decreasing, or the requirement of the energy. For instance, I have to move a point charge from one particular position to another particular position. Therefore, in what rate I have to increase the energy? It is like in other words, it is a kind of acceleration type here. So the potential in order to calculate potential gradient, sorry. So the potential gradient can be easily derived from the earlier expression itself. So we already know the potential at a particular point is nothing but the integration from the line. So if it is from the infinite point, then here it will be coming with infinite. So that's the difference. And the corresponding electric field and the line joining vector. Okay, so that is what the so the dot product will become a scalar and net result is a scalar itself. So this is the same expression we have used, and now we are actually taking the differentiation with respect to this dl. Therefore, we will get the simple expression. In other words, it is nothing but the electric field at the one particular place, the electric field at this particular place, and this particular place. This difference is nothing but the potential gradient. So that is what the potential gradient. This is actually written in terms of line vector, but in order to calculate everywhere, so it is better to describe them in a coordinate system. So here it is taken with a Cartesian coordinate system. So if we define the potential in anywhere, then we can easily calculate the potential distribution, and that potential distribution will be having potential gradients. And so we have to differentiate in terms of x, y, z directions. So that is what it is done here. So the change in the potential with respect to the direction. So here you know about what is meant by dou. So it is a partial differentiation. And by the way, you will get the corresponding dx, dy, dz quantities also will come into the picture. So this also tells about that in a given short distance or given a short space of place, how this potential distribution is available. So this all very much useful for many computational applications. For instance, you want to design a antenna, you want to design a mobile phone or something, then you have to calculate the electric and magnetic field just around that. So we need to use computer simulation code. And in that simulation code, if we know the potential distribution, we can easily calculate that. So sometimes some of the complicated shapes will be very tricky to solve with these differential operators. For that, we have to use some numerical methods like Newton-Raphson method, block methods, or some other even for time-dependent applications. Then we have to go for a little bit higher order mathematical expressions which solve that. So that is what the simulation tools which we see nowadays. So that all using this fundamental operators, which we call del operator. So by the way, this del operator, we already know about that. So that is nothing but dou by dou x plus dou by dou y, and the corresponding operator will come. So this will give the field expression. So we know about that. This is a vector. So therefore, the electric field also will be the vector. So the negative sign will be always there. So the meaning of the uh, negative sign, it tells about the electric field is always directed from higher to the lower values of the V. So that is very obvious that the water will flow from higher potential to lower potential. The very similar potential concepts can be applied here. Okay. In fact, I always mention that in many places I have mentioned in my class that water and the electric field is almost same. Okay. So then the curl of the curl of the gradient is always zero. So this clearly indicate that. So we know about that. This is electric field, and this del cross E is already zero. We already know about that. It is because the electric field always will be emerged perpendicular to the surface of that, and therefore, if you calculate the curl of that, the curl of the is nothing but calculating just around that what is happening. So this anyway it is going to be uniform. In that case, there is no change with respect to the circular aspect. So therefore this clearly tells that this electric field whichever is induced supposed to be by a scalar quantity. So this del cross um gradient of any particular scalar quantity will clearly tell about the behavior of both the scalar as well as the resulting electric or the I'm sorry, the vector itself. And then yeah, this is very interesting that whenever we struggle with Coulomb's law as well as Gauss law in order to find the electric field or particular one, then this gradient one will give more precise as well as accurate one. But one has to be good at mathematics in order to solve this little tricky mathematical procedures. And that is why actually Coulomb's law and Gauss law mostly people use if it is a regular geometries like line, if it is a sphere one or cubical one. In that case, people easily solve it with Coulomb's law or Gauss law. But whenever it goes with something new shape, for example, you want to calculate the uh, electric field induced by this line, which are changing its characteristics in a periodic manner. So in that case, it is very difficult to use Coulomb's law or Gauss law, but with that this kind of operators we can easily calculate. So in fact, with operator it will be more accurate as well compared to our derivation methods. And the other very important aspect of these three components of the electric field, that all these three directions, they highly depends. We think actually they are highly depends on each other, but there is no. They just participate whenever this operator or multiplication or something else will come into the picture. So these are the things we have to understand from the potential gradient. And here is a simple example how to calculate the potential gradient, and therefore we can calculate the electric field. So in a particular region or a potential distribution everywhere in a given space is given with the expression, and here it is one-dimensional one. So along the particular x-axis, how this potential is distributed, like that it is given, and we have to calculate the corresponding electric field because of this potential distribution at x equal to 2. So at x equal to 2, what is the value? So that is what we have to find. So the question is whether it is equal to 0 or greater than 0 or less than 0. So I missed out something like this. Okay. So how to calculate that? We know that fortunately we have the value of V, so we can easily calculate the electric field. So how to do that? First we have to calculate using this del operator, and this del operator is nothing but dou by dou x and dou by dou y and dou by dou z vector. And since it is a one-dimensional one, these are not required. Just we have to differentiate with respect to x-axis. So we are going to differentiate only with respect to x-axis, and the negative sign, we know that why it has come. And when we do so, then we can easily get this. So just we have to find the differentiation of that. And we got the electric field. Okay. So, and in order to put the vector, then we have to put this AX vector. That's all. Okay. So now we have to calculate the magnitude of the electric field at x equal to 2. So you have to substitute x equal to 2. So if you substitute x equal to 2 here, it will become 12. And if you put here, it will become 4, then it will become 12. Therefore, you will get Ex equal to 0. So the answer is equal to this. So your quiz problems most probably will be like this only. Okay. So about 5-step or 6-step, finally, you have to calculate the value. There is another example. So the potential gradient is given in terms of the Cartesian coordinate system. So it is going to tell about with respect to the origin point at a particular distance r with respect to theta and phi direction. So everywhere else, how this potential is distributed. You need not to wonder. This is very similar expression will come for a simple wire antenna. So you just to take a wire and connect with the oscillator and put a ground plane. So this is we call monopole antenna. This monopole antenna most probably will get this kind of a potential distribution only, and therefore it will give corresponding electric field. We can easily see that. So only thing is this is time dependent. This is a time independent. That's all one. Okay. So so here you can see that we have to calculate the electric field, electric flux density. We have to calculate at this particular point. So we already know about that. D is nothing but epsilon E, where this epsilon is nothing but epsilon naught epsilon r. And if nothing else is given, you can assume this value equal to 1, and therefore epsilon equal to epsilon naught itself. And by the way, we can easily calculate the D value. So we know that electric field we can calculate from this gradient of the potential. And once the potential is once the electric field is calculated, then we can easily integrate to calculate the you can easily calculate the to get the potential energy for a given charged body. That is what we are going to do. So here, first we have to calculate this electric flux density, so which is nothing but epsilon naught E. So we know that this electric field is nothing but this minus of del V. Okay. So the minus symbol is here, and the del operator is used. So you have to remember this del operator, and since it is open book test, so in fact, most of the while you do the exam, you can keep this worksheet ready for formulas and all the way, and let it be this del operator be the first one, because in many places you will use this del operator in future. Not only here in magnetostatics, as well as in time dependent cases also we will use that. So this del operator, so we have to use this del operator and we have to do it. Okay. We need not to wonder about that. This expression look a bit tricky, but once you have substituted that, the answer it will be very, very easy. So just you have to remember this. Yeah, we can easily first we have to differentiate with respect to r, then with respect to theta, and with respect to phi. So you can easily remember here it is, and there is nothing in the denominator, but here r will come. Here r sine theta will come. That's all. You can easily remember actually. So this is all this del operator. If you remember, then this remaining future del square, all these things also you can easily remember. So once this is calculated, so the electric field is calculated. and we have to just substitute the number. So this is r, theta, and phi. So when you substitute that, you will get the value. And here, once again, you can see that these two value become 0, which means that only this r vector survives, which means the antenna, this particular structure going to radiate equally in all directions, and irrespective of the uh, theta or phi. So that is the interesting property of this particular antenna. And we have to calculate the work done, which means the potential energy. Particularly, we have to calculate the work done by that. So the work done we can easily calculate. So since we know the electric field, if we take the if you know the line vector, then we can easily differentiate with respect to that. And if it is a one-dimensional one, we can easily do that. If it is a three-dimensional one, we have to do it in tricky way. So first of all, we have to see this line vector, whether it is one-dimensional or two-dimensional. And here you can see that we have to move this particular point from here to here. So how to find it is a three-dimensional one? You can see that each value, and this all the values are going to change. 1 to 4 it is changing, 30 to 90 degree, and 122. So in 360-degree direction, it is going to change the value. Okay, so in other words, if this is the vertical line, and so initially it was here, and then some 30-degree it is something here, then suddenly it becomes 4 and 90 degrees. So 4 and 90 degree will be here. So like that. So this is a three-dimensional problem. So it is the best easiest method is if you do 3 times integration, then you can easily get that. There is nothing wrong in it. We already know about that. In any particular field distribution, if you want to move from a particular point A to B, then you can go in straight line. You can go in any way, in any possible way you can go, but the total energy or the total work done will be always be same. So VAB equal to VBA, and only minus is the means the only the direction is the only. So otherwise, from if you add from here to here, here to here, here to here, so that is what it is done over here. So first we have to calculate this line for A to A dash, which is changing only in the R vector. And here it is varying only with respect to theta. So let me mention that this is R vector, this is theta, and here we are going to vary only phi. So this and moreover, these operators are very easy to mention. So this DL operator, and here it is dr AR vector, and DL vector for this theta wise, it is R theta, and with respect to phi, it is R sine theta d phi. That's all you have to substitute here, and we can see that the corresponding operator alone will come into the picture. Therefore, it is very easy to differentiate, very easy to multiply with this electric field and get the integration done. If you do simultaneously also, it is up to you. So it is done, and we have calculated the potential energy over that point. And here that work down is done with, and keeping other values constant, and it is done. So after substituting that, you will get the total work. And by the way, when you multiply this charge Q value, you will get the total energy. You have to mention in terms of joules. So this is very, very easy procedure, but still easier one is applying the potential. We already know about that. This the total work done is nothing but the Q into the potential difference between the point A and B. And we already know about V, okay, because V is already given here. So since the V is given, just we have to calculate VA and VB and find the difference between that and multiply with Q. That you will get the potential, sorry, the work done will be there. So we already know about VA, VB. So VA, we have to calculate. VB, we have to, I'm sorry, VB, we have to calculate first, then VA, find the difference. And then we have to multiply with 1 microfarad Coulomb, and you will get the same answer of that of here. And another exercise problem is given in SEDQ, and the answer is also given. So just check it out. Just try with a very similar manner and get practiced. These kind of problems are very, very simple problem. Okay, so doing this procedure is very easy. Doing this procedure is easy. And doing this step, this step, this step, all these steps, they are very easy. But the tricky part is managing the time. So you have to do it everything properly, neatly you have to do. And somebody they will keep on strike and do, and it irritate the evaluator. Evaluator means I'm the evaluator. So generally it has to be done in a neat way. So that is what will take time. And in the exam, more than your intelligence, your time management skill is very, very important. So this kind of the problem is simple by individual steps, but it is in size, it is big. So my professor used to tell this problem that a person walking from for a 1 kilometer, it is very, very easy. And he is going to use the same step for 100 kilometers. So it looked like a very, with respect to the small steps, it is very easy. But for a large stretch, it is very difficult because we'll become tired. So this needs good practice. Like running 100-meter dash is much more simple rather than a marathon. So these kind of problems are very, very simple. Like this, actually, many problems are there in the electromagnetic field theory. So that is why these problems they look very complicated in size, but they are by method it is very, very simple. Basic mathematics. And interestingly, so far now nobody asked any questions about the numerical problems all the way. This clearly tells that uh, you haven't started doing any problems as of now. So that is what uh, my understanding. Let me put a simple question. Do you know why so far now uh, you haven't seen your own time inverted version? For example, in future you have found new time machine, and therefore, if you have invented the time machine, by this time you would that person that person means you only. So you will meet yourself by today or yesterday or sometime. Okay. So why it is not done so far yet? Do you know that? Can anybody answer for this question if you are curious about this time machine or time travel? Just think and tell. I hope you got the question. So you are here today, okay? And after 20 years, somewhere else you found time machine, and but you haven't visited today's time from future, and or you haven't found anything and you haven't traveled over the time. So what are the possible ways for that to tell that why you haven't visited your future one? Anybody try just at least?
Sir, I think that if I will make myself back, then I will become lazy afterwards
Yes.
because I know
Hmm.
I will find one day and then I will not work on it.
Okay. Yes. Yeah, that could be. Yeah, that's a great one. Yes. Or you haven't found. That is why you haven't come back like that. That is also one. The third one. Anybody else? That's really very interesting answer. It seems like nobody is interested in time travel. Okay, fine. Um, Even actually, I always think about this time machine, all these stuffs. I used to tell myself that if I found in future, then why I didn't visit it today? Because we always come back if the day is very crucial. Okay, so if, for example, I met an accident means, then I will come back in time and I will advise the person that don't go in that direction, or in a particular exam I failed, or then I will come back and tell that do the steps and solve it like that, of course. And so far now in my life, such a great disaster or some mysterious situation didn't come so far now. So that is why uh, that particular person or of myself didn't come. That is what I think. So like that. Okay. So just why I asked this question, because you people haven't uh, started, and in few days you are going to get face, and in another few days you will be going to get. So assume that you found time machine, and you one day you think actually in electromagnetic field theory I didn't get good mark. So you just come back and yourself just advise, means think yourself that we should not do the splendor and let's do it well. Okay. In other words, we can say that by time machine you have come back to today and you got some good advice, and you are going to do well in exam. So further the practice is very important, and so kindly try. Okay. And whatever the questions you have in mind or anything, you can always ask by phone or Teams. Of course, in future you will see that yourself. Many of you are going to ask me that I didn't, I haven't done quiz well. Can you, can I try again, or can you give some assignment? I will do in better way like that. You just to see yourself. In future you will ask. So better we will avoid that. Okay. But that's what I won't do that. That is what I am indirectly saying, that I won't. I mean, I won't encourage such activity. If it is supposed to be done, it's supposed to be done for everyone, and that is not possible. Okay. Okay. Now we will go to the next topic in the same concept, in the same concept of uh, divergence itself. The advantage of the divergence is like it can readily can give the electric field if we know the potential. Okay. And in many situations, particularly in the real world situation, the amount of charge density is also very difficult to estimate, and the field also very accurately to define. Okay. But in when these two things are not at all available, then is there any third possible way to acquire this electric field or charge in any other way? And of course, we have the solution, and that is often referred as boundary value problems. And this is actually very, very practical one. And can someone say that what this device is? Someone studied about this device? Anybody else? What is this device? Can you recognize this device? Anybody studied semiconductor devices? Yes? Yes, please.
MOSFET.
Yeah, great. So this is actually called metal oxide semiconductor. The gate will be metal, and this is oxide, which is an insulator, and this is semiconductor, often referred as MOS, and this is a field effect transistor, so MOSFET. Okay. So, and this kind of device, inside that, what charge density is available, that we do not know sometimes. And at the same time, since the charge density is available, it is very difficult to calculate the electric field. And at initial conditions, let's say that at voltage equal to 0, no voltage applied, but you will wonder that the electric field will be still available. And I think those who have studied semiconductor device, they will always say that as a built-in potential. Uh, and that is the potential responsible for cutting voltage, all these things. So such a calculations can be done with this kind of boundary value problem, and that problem starts with calculating this potential gradient only. And for this we should know the boundaries. So here the boundaries are, three boundaries are there, and in these three boundaries we can apply the voltage. Okay. So here maybe voltage is equal to 0, here maybe voltage is equal to 1 volt, and here maybe 3 volt or something. Then What about the electric field? Immediately we can calculate by setting up this, and that is what we often refer as boundary value problem. And for this, we have to learn this Poisson and Laplace equations. And Poisson and Laplace, they are actually great French mathematicians, and they worked after Newton. And these two people often referred in their own places as Newton of France, like that. So, and they worked in many aspects in the thermodynamics problem as well as electrodynamic problems as well. And in particular, Laplace, he has worked in many great ways. And so people used to say where Poisson don't work, Laplace will work, like that. And Laplace will work for all the places. So we will see why it is often referred to. And these two Laplace and Poisson equations, which are used in this boundary value problem, more likely for these kind of tricky structures. Because if you apply this Coulomb's law or Gauss law for this kind of structure, almost it will take 100 years to solve the problem. Okay, but in case of this boundary value problems, it is very easy. So that is why the problems which are very difficult to work with this Coulomb's law, Gauss law, we can apply this gradient method. And by the way, we can easily get the very important informations like the potential energy to move the charged body. Let's say that I want to move this electron from here to here. So what about the total energy required, which is nothing but the potential itself? And the problem mostly work with the potential domain itself, and the result are nothing but electric field. From the electric field, we can calculate the charge density by using Gauss law and all the way. So these three methods, Coulomb's law, Gauss law, and as well as the boundary value problems, they are actually, we can say that at least by application, they are orthogonal to each other. Whenever that is one is not working, we can go for the alternate method. But in present day times, for with computer simulations of many complicated and multitasking, like there are capacitor inductor together if it is available in a nearby places. For this boundary value problem will give better results. So first we have to derive the expression for Laplace and Poisson equation, then the problem become very easy. So it is very easy to derive this Poisson and Laplace equations. And we already know about this Gauss law. The Gauss law tells that the charge density is equal to nothing but the flux density itself. So that is what it is given by this dot product of the del operator, which is nothing but the divergence. So this del dot D is nothing but the charge density, which is Gauss law itself, in which we are further defining in terms of electric field. And we already know about the electric field is nothing but the potential gradient. So we are going to substitute this here. When we substitute this here, then we will get this expression. And this is what we often refer as Poisson equation. And here we are considering for inhomogeneous material. If it is a homogeneous material, then you can take this because this epsilon become independent of XYZ axis. So you will get epsilon del square V will come. So that is anyway negative will come, which is nothing but the charge density itself. So that is, for example, for a if you take some water and that is a homogeneous material and this equation applies. But for this is actually this is completely inhomogeneous material. Here it is different dielectric constant. This is a different dielectric constant, and for metal dielectric constant is 1. Like that, some different conditions are there. And yeah, for homogeneous medium, we can write like this. And the Poisson equation, this is what we call Poisson equation. And if you take the special case, when the charge density is equal to 0, and you will get this right-hand side becomes 0. And that is what we often refer as the Laplace equation. So Poisson equation and Laplace equations both are same. And the Laplace equation is the special condition of that. And for instance, in case of oxide, it is an insulator. So they won't be having any charges. But in case of semiconductor, they are a dielectric material plus they are having charges. It may be positive type or P type or N type. It is a semiconductor, so they will be having charges. So here we have to apply Poisson equation. Here we have to apply Laplace equation. And so applying both the equations to solve the electric field in a inhomogeneous medium, it will be tricky. So that is why we have some special tools. And this operator which comes with this del square, and it is often referred as Laplacian. So this del square V in this Laplacian is nothing but the squared version of that. So in this squared version, we supposed to it is nothing but uh, del dot del itself. So for that XY Cartesian coordinate system look easy, but this other things will become very tricky. So this also you try to write in your notebook in the beginning itself. And this is actually very, very useful and huge. In fact, Maxwell's very first work in his young age, he used this Laplace operators to calculate the thermodynamics of Saturn, and he found how this means in the Saturn, how this rings are formed, whether the ring is continuous water body or they are nothing but some kind of lines, magnetic lines or something else like that. But he said, no, no, they are nothing but small particles. That is why they are orbiting in this way, like that he proved. And he used the simple Laplace equations only for that. And even actually in semiconductor device physics, you will first study with Poisson and Laplace equation, then continuity equation will come. By solving, we call actually this simultaneous solutions when we do, then we will get the current and we can see how the current is flowing inside the device. So that will be very, very interesting theory. And the simple way to apply the Laplace equation is like once the problem is identified as the Laplace means we have to apply the Laplace equation by simply considering this charge density is equal to 0, and therefore we can easily apply. You have to take differentiation 2 times, then you will get 2 constants, and you have to identify the constants. For this, you should know the values. So for this, at least we need 2 boundaries. So 2 boundaries may be anode and cathode, or if it is you are having 3 electrodes, you will get still better way. And so you will see that 2 boundary conditions by applying this, let's say V1 equal to 0 and V2 equal to 3, like that. Then if we apply, we can calculate this M and B. So that is the ultimate thing. Then we will get the electric potential. So potential, if it comes like 3x plus 4, then we can easily calculate the electric field out of that. So we have to find the differentiation of that. The electric field become 3ax vector, like that it is going to come. And there is no local minima or anything else. And these are the means the boundary is the which we call actually minima or maxima of the given particular problem. And the remaining values can be easily calculated by means of stepping by average method. So this is often refers Newton-Raphson method. And in case of electrostatics, the most two important ones like resistance and capacitance we can easily calculate. Let's see how to calculate the capacitance for different structures. So here is a very simple example. We are going to take 2 parallel plates. Okay, there are 2 parallel plates, and they are separated by some dielectric material. Okay, let's say silicon dioxide. So the silicon dioxide has the epsilon R of 4. 3.9 is the precise value. Okay, so this if it is separated by some dielectric material which has the dielectric constant, and in one side it is going to be grounded, in another side we are going to connect with the battery like this V0. Okay. So in that case, we have to calculate the capacitance of this parallel plate. So that is the objective. And we know about that. The capacitance is nothing but Q by V. So we have to calculate the total charge density and for the applied voltage. So first we have to calculate V, then we have to calculate Q. So from V, we can calculate, sorry, from the boundary value problem, from the boundary condition, we will calculate V. From V, we can calculate electric field. From this, we can calculate D. From this, we can calculate the charge density. let's take this a volume charge density V, and then we can easily calculate the Q. So this Q and V, when we substitute, we will get the answer, that is capacitance volume. So that is what we are going to do. So let's see how to solve the boundary value problem. So with respect to the given condition, we are putting in a particular axis. So here, in order to solve for, instead of solving for this entire sheet, so we are going to solve for only this two line alone, which are oriented in the x-axis. So that is what it is drawn here. X equal to 0, x equal to d. D is nothing but the separation distance, thickness. You can call it by any name. Okay, and at x equal to 0, we got the potential equal to 0, and x equal to d, potential equal to V naught. So these are the two informations we have in hand. There is no information about charge density or anything else. So since it is a dielectric material, we are going to assume, often people refer this as a lossless dielectric material, which means that there is no charge density available. In that case, we have to apply the Laplace equation. When we when there is a charge is available, then the problem become trivial. So we have to assume something, then we have to work out. And so we need initial conditions also. But here such initial conditions are not required. So here we can easily say that first we will actually solve with first integration, then second integration we are giving. So we will get this. So this is a general solution, and this general solution should be solved. And I believe you people are great and working on this. First, we have to supply what is x equal to 0. When you substitute x equal to 0, you will get b, and this b is equal to v of 0. So v of 0 is 0, so b equal to 0. And we are substituting x equal to d. So when you substitute x equal to d, and you will get ad equal to v naught will come. So therefore, a equal to v naught by d. So v naught by d has come. So here we are going to substitute 0. Here v naught by d. So we will get the electric field. So the potential we got. So the potential is, we can say that it is going from 0 to v naught by gradually increasing. So this is why this is how, and it is going in the rate of v naught by d along the x direction. And in fact, one can say that this rate of change is nothing but electric field. So that is why actually people used to call the electric field is nothing but potential divided by the separation length d, like that. Then we can easily apply this procedure to calculate that. So once the V is calculated, then you can calculate this electric field, then you can calculate D, then you can, from this D, you have to calculate the magnitude of that. So with respect to the vertical direction, vertical means the perpendicular operator, if you take, that will mean nothing but charge density, and that will give the total field. That's all. So here we have the V, and first we apply the del operator. We are calculating the gradient. So the potential gradient is nothing but electric field. So while substituting, we will get that. We're supposed to be very careful about this vector. So this is on the line vector. So on this particular line, we are actually calculating. So this operator also will be having the same. Sorry, this vector also will be having the same unit vector itself. So we got the electric field. Then we have to multiply with this epsilon. So where this epsilon, I already told, epsilon is nothing but epsilon naught, epsilon r. So in general, we call that as a epsilon. That is called permittivity. So this d epsilon e, and that is simply we are going from here to here. And this magnitude, if you take this magnitude, that is nothing but this ds, which is nothing but the vectorial field component. So we calculated the normal vector, and that is isolated, and that is going to be the charge density. Once the charge density is available, then we have to do the integration over this distance. So it is very simple. Just we have to multiply with this d, and if there is a area, so we assume that we have this area A, then we have to multiply that so that you will get the entire volume itself. So we can easily say that this Q is nothing but rho s into A into D. Yes. Okay. So here we have to take only the surface, of course. Yeah, only the area alone we are calculating because it is the only surface is coming into the picture. That is why it is multiplied only with this surface. Then we have calculated the total charge. Okay, the total charge is, so the rho is known. Just we have to multiply with this A. And here it is done with S. So I think you can easily understand that. Yes. And now we have to divide by this V. Okay. So when you do it, V is nothing but V naught itself. That is a potential difference. So here this V is nothing but VAB, which is nothing but V naught itself. When you substitute this, V naught will be gone. Then you will get the epsilon S by T. Okay. So that is nothing but capacitance. And the famous expression for capacitance is nothing but C is equal to epsilon naught epsilon R A by D. And here you can see that there is no expression about the potential electric field, nothing else is there. Indirectly, it means that a parallel plate, theoretically, it's supposed to have a constant capacitance for the applied voltage. If this is capacitance, then it's supposed to be straight line. But interestingly, most of the dielectric material will show kind of a curved shape. Okay, so this is what people used to call, this is a very important uh, identification. People found the capacitance is potential dependence. That means what? The dielectric A is constant, D is constant, epsilon R is constant. Only this epsilon R is a potential dependent. And if it is potential dependent, then something there inside. And that is what made the people to think much more in detail in the molecular level. In fact, the very first molecular level study being done with the polarization. And till date, many debate is going on this particular field because of this crucial, interesting part. We can also apply for the other things. Maybe in the next class, I will tell how to do that. And there is a interesting uniqueness theorem is available. We will see in the next class. Thank you. If you have any questions, please free to ask. You may leave now.
Sir, what kind of questions will come on quiz? Could you say again? Like what kind of numericals?
That's what in the electrostatics, whatever that I taught, from that it will come.
Yes, sir,
How
like
we can
higher
pinpoint.
order or
Uh, okay. Oh, higher order thinking or simple questions or something that is okay. Assume higher order questions. Okay, so most probably that is what within the scope of the given topic. You have seen that I have given example and practice questions, and it will be very similar. I will be teaching with cylindrical coordinate system, but in the quiz it may come Cartesian coordinate system or some spherical coordinate system. That is a minor difference will come. The concept is going to be same. Nobody can't change the concept. Once again, I'm saying
okay.
I'm going to give some one minor tips for you. If you want, you can listen. Otherwise, you can leave the class. The very important advice, even one of my great professors told this, like in order to solve this, in order to understand how these questions would be asked in the exam, you need not to ask the professor itself. What you can do is, let's say that there are 10 topics available in a particular unit, and each topic you just frame number of questions, identical, non-identical questions you have to prepare. Let's say each topic you are preparing 5 questions. You have to be very honest by yourself from the scales like small to big, like that. You just make some easy to, first you have to refer the book, then you just come with original problems, and for those problems you just to make the procedures ready. Therefore, within 1 or 2 days itself, even before studying for the course itself, you will get 50 questions in hand. And the professor is very simple enough that he could ask questions within that 50 questions only. So by this way, you have cracked the question paper by yourself, which we call brute force attack. So you need not to worry about that. Okay. So you have the question paper with you, and then you have to practice how to answer for that. And I will be helping in that part. You just solve any of the particular problem by yourself. Even if it is an example problem, you solve. If you find any difficulty in that, or if you feel that, sir, this step should be included or not, because the mathematics exam is not about the answer, it is about the steps. Similarly, electromagnetic field theory is also same way. So And when you do rough work also, you always put the operator and draw the proper diagram all the way. Such a practice is required. Your hand supposed to be practiced with that. In the exam, it's supposed to come in fluent. Not only for this exam, not only for this particular course, all the courses, whenever you do that, you just always complete it. Some people will, for rough work, they will do simply, let's say, they won't write the operator, they won't write the vectors, or if in some other problem, let's say some other course, you are studying electronics course or something, in that if you are solving for Boolean algebra or something, some people will be very lazy about that. But don't do that. You always practice with the same thing what you are going to do in the exam. Okay, then only you will understand. You can feel yourself whether you are doing in a right way. At the same time and the energy required, everything you can easily understand it. So always practice in this way. I think this tip may be helpful to you. And so hereafter, don't ask whether the question, what is that question all the way like that, and don't underestimate any exam as well. So always think it is a higher order and the problem is solved. But I appreciate that because you should prepare in that aspect. Okay, so if I just want more technical questions rather than this questions like very general about the exams all the way. Okay, so you just solve the problem and take photo of that and send me. I will appreciate that. Okay, let's see that before quiz, how many of you are going to ask questions?
Okay.
Yes. Yes. Thank you. Thank you all.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.